So AI instructors, is that what it is?
Yeah, training.
Are they any good?
It pays a lot.
Oh, wait, how are you getting paid for it?
Because it's through Handshake. They got a contract.
You're training the AI.
Yeah.
Oh, I see. So along with a bunch of other people, which I assume is the short-term job, because once you're trained, you're done.
Yeah. But they have multiple projects.
Huh, should I be doing that?
You should. $125 an hour.
How much? 125?
Yeah. Are you good with Copycat?
No, I mean, I used it, but I would like to get good at it. You're good with KiCad?
No, Inventor. Usually 360.
Oh, 360 is horrible. So talk about designer bloat. I mean, they tried to make a one-size-fit-all CAD environment, which is just the stupidest thing in the world. They bought Eagle, which was great. And then they ruined it by implementing it into 360. I took a class on it. I'm like, I'm never going to use this.
I used it for 3D printing. That's all I used it for.
But not for PCB layout. But... All right, so more than 18 here. 4, 6, 7. We have 8. Huh. So I don't know what you're all doing this semester or last semester, that you're all here this semester, but it's kind of open for a small class. I suppose half of you want to drop. No, just kidding. So we're here for EMAG. Hopefully everybody's on the same page about that. I don't think there's anybody here that doesn't know me. Is there anybody that doesn't know me? Oh, yeah. You've had me for plenty. So not a lot of storytelling to talk about myself. Actually, I mean, it is, no, this is the wrong file. Apparently I'm still in ETAG. Huh. Now they corrected all those things. Small edit needs to go in there. This is the first class I ever taught. Actually, EMAG back in, I don't know, 1999 or 98 or something like that. So before you were born, I taught this class. In an interesting teaching style, we had a studio style, which is 3-hour classes. Experiment and class was intertwined. So interesting, but I find it interesting. You probably don't care. Anyway, so we're here. You obviously made it to class. You know where class is. Laboratory, or we have a 3-hour laboratory on Friday. I'm really bummed about that. I suppose many of you are as well. Mostly because it's ski season, and then end of the semester it's paddling season, and I really don't want to be here on Friday. It's all about my selfishness. But let's say it is what it is. If you talk to people who have taken the class with Dr. Axoy, he uses his recitation section. I actually try to kind of run laboratories, so a slightly different environment. Or if you started with him before, I do things a little bit differently. I edited all this stuff, so some of these things aren't correct. So my ops hours, a couple of you heard this already. I will be on the main campus on Mondays and Wednesdays. Those are my official ops hours. I have to report those for ABEC considerations and all that stuff. So that's what I included in the syllabus. That said, most of you know me well enough that if I'm in my office, then you're welcome to come in. No reason for you to go up to the main campus unless you happen to be up there Monday, Wednesday morning as well. So you're welcome to stop in there. But otherwise, feel free to drop in my office. Open door policy indicated there. This is in the Brightspace. So my schedule, there's my schedule. So my teaching schedule, you're blue, dark blue, I suppose. So that's when I'm here. I have circuits in yellow and electronics in green there. And my official office hours in light blue. So apparently not in my office as much as I have been in the past, but for the most part, Monday and Thursday afternoons will be around. You can certainly find me in the laboratory sections. We're kind of short on TA hours, so I'll probably be spending most of my laboratory time in the laboratory. for your class and other classes. So you can find me there, though priority will be given to those students. So all my laboratory sections, including yours, are in 102, which you're all well familiar with. There was that on the registration, it said we're in here for the laboratory. That is not correct. You may have gotten an email about that a couple hours ago. So officially that's been changed. We'll be up in 102, but not tomorrow. That's on the calendar. We will not have lab tomorrow. Not much to do tomorrow. So that said, kind of things you've seen before. So again, feel free to stop by. We do have a TA, not again, a little bit more background than you care about. He was a 5-hour TA, now he's a 10-hour TA, so took a little pressure off me there, but he'll be doing all the grading, so the laboratories, all the grading associated with homework in laboratories. I suppose just to mention, if anybody has any questions, by all means, fire them away, just let me know. So this is EMAG, Physics 2 on steroids, I suppose. So if you like Physics 2, this is going a lot more detail. We do a lot of math in this class. So that relates to, I think it's called multivariate. So is that what they call it at Albany? Lose track. So we'll be doing double integrals, triple integrals, vector integrals, that type of stuff. It boils down to simpler equations, but that's the fundamental background of the math that we will be using. On the same token, all this corresponds to visualizing things in 3 dimensions. So, which is a very difficult thing to do. Most people don't do that well. I don't. I'm horrible at it. So one of the things we will actually work in the laboratory is how do we look at 3-dimensional fields, vector fields, and how do we project them into something that's 2-dimensional and kind of do that mental manipulation to visualize them in 3 dimensions. So I think it's non-trivial. If you're kind of artistically prone, maybe it's a little easier for you, and that's great. I suppose you've all taken circuits, so no reason to emphasize that point. I think most of you, it's been a while. The relevant part of circuits will be the phasor analysis that we did in Unit 2, if you remember circuits at all. So complex exponential arguments. But actually won't do that until near the end of the semester, but it is something that comes into play here. And again, the math. Comments about academic dishonesty, I suppose. And again, you've heard me say these things before. You could read through this in detail, I suppose, if you want. Other instructors have talked about it, but my TLDR version is if you cheat on a test, test is over. I give you a 0, I don't care, and I fail you in the class. Tests are things of significance. Cheating on tests is not viable, or not something that I find acceptable. I should say it's viable if the students have done it. Outside of that, in terms of things like the homeworks and the prep assignments in the laboratories, I have no issues with you working together. Actually, I would prefer that you worked with others. Engineering is a collaborative environment, and finding people to work with makes both class more fun and college itself more fun. That said, working together doesn't mean like I don't get this at all. Can I copy your answer? So I usually don't have time for this, but if I find homeworks that are submitted exactly the same, the TA brings it to my attention, I'll do both zeros. I don't care who is the source of the material. That just shouldn't be happening. You should be writing things down in a way that's meaningful for you, even if the answers are consistent with someone else's answers. Not everybody thinks the same way. You should be presenting work in a way that represents how you understand it. So, I guess it bears mentioning now more and more, and that you're welcome to use ChatGPT. I guess it's getting smarter and smarter. It's also getting stupider and stupider. I find AI actually being more and more annoying as I see it pop up in Google and stuff like that, because it seems wrong more often now. I don't pay for a subscription one, so I suspect that's probably a little better. I don't know. Anybody pay for one? One pays for one. With that said, I'm not against your using ChatGPT for supplemental instruction. I will say As you probably heard me say before, that I am your best resource if you get stuck on doing homework or things like that, because I'll make you work to understand the solution as opposed to give you an answer. And that's the learning experience, taking what you know and working through it and getting that answer yourself as opposed to something like ChatGPT. I don't know if we'll have a peer tutor for this class. That's out of my hands, but it's someone else that will giving you an answer more directly. It's not particularly helpful. It usually plays out on the exam if you use ChatGPT for the homework or any of them, I suppose. Though I did find out earlier today that the Twitter AI tool is the scientific one. So if you're going to use an AI tool to think for you, use the Twitter Grok, I think it's called. Use that one. So get the best one that's going to give you the best answer. Of course, ultimately, when you take the test, you can't tag Grok in or any of them others. So the test is yourself. And if you fail the test and you used some sort of AI tool to do your homework, I'm just going to laugh. So it's not, not a learning environment. I do think you should be using it. In this class for our laboratories, reports are a little less formal than I would have hoped that you submitted for electronics and circuits. There was a theme. You should be discussing things in the theme. This is a little looser, I suppose, a little bit less theme driven. You should still use your words though. So same thing I say to my nephew when he was 6 years old. Use words to describe what you see. You should be writing complete sentences, things like that, describing what you see, but it doesn't have to be a deep introduction or deep conclusion. But in that case, I still recommend that you actually do use an AI tool to help you write, because most of you need improvement in your writing skills. Per what I said to the circuits class yesterday, most of you have historically written like shit. Hopefully you've gotten better now. They've had a little bit more exposure to it. But it's a skill that you need to develop. That said, you are going to develop in tandem with some sort of AI tool. That's not going away. I hope that, when you go off and have an internship this summer, which everyone I hope has, or if you're graduating a full-time job, that you use something to help you write, because why wouldn't you? I mean, that's what it's there for, save you time. Moving on, the summary of that is don't cheat on a test and try to learn. We have a textbook associated with the class, David Chang. I think it's actually the same textbook I had when I was different edition, but same author from when I was an undergraduate. So I've had a copy of Chang for decades. Again, I have copies of Chang that are older than most of you, which makes me sad. It's a fine book. There are good electromagnetics book. There's a bunch of them up on that bookshelf. So I assume everybody's seen that up on the third floor. Every one of those books is one I brought in. There's a bunch of EMAG books in there. There's some that I don't particularly like, just because I think they're simplistic, but they're not bad. I do like a level of sophistication, and I think Chang is fine. I don't know if Chang is out there or not. I think I have 1 or 2 copies in my office if you want to see it. We'll be doing prep assignments like we did with electronics and circuits, hopefully more often than not. And homework will once again be twice a week, so you have that to look forward to. And all the comments about laboratory and exercises that we'll be doing on Friday. I will say something that's a little bit different in this class, given the way I break down the units, and I'll bring up the calendar and you can see that. I thought about doing this as a separate unit, so I may change the schedule or the calendar a little bit, not in terms of dates, but in terms of the labeling. We'll open up with some discussion of mathematics. So as I said, we do a lot of vector mathematics, and we'll review some of those concepts in this class. I don't expect you to memorize any of the curl equations or divergence equations. We will be looking at 3 different coordinate systems. The expressions are fairly messy. Other faculty have, and I'm not pointing out anyone here at Albany, I mean, in general, I've come across faculty who expect students to memorize equations like that. I think it's stupid. I'll give them to you. So I don't think there's value in memorizing complex cylindrical coordinate gradient expressions. I don't know them off the top of my head, so they come back relatively quickly when I look at them. But it's been 2 years since I taught this class, so I can't say that things drift out of my head as well. So we'll open up with some discussion of math, and then we'll journey off into electrostatics and then magnetostatics. Electrostatics will have a task. Magnetostatics will have a task. Maybe we'll do a little mini quiz for mathematics just to make sure that we practice enough, and then we'll end with plane wave propagation with its own test as well, and transient electromagnetic behavior. So we do have 3 exams. They're broken up in 3 units, and I suppose again the mathematics being a mini unit by itself. As such, our 3rd exam is, I guess, technically, maybe I'll change that. I have it on our last day of laboratory, which is the day before, class day before the last day of class. So I suppose that would, in some sense, make the last day of class a little bit meaningless. That said, I do offer an optional comprehensive final. So if you've tanked the 3 tests and you want to make it up for it in the final, I will qualify that a little bit, give you some feedback. But you can opt into the final, and we could use the last day of class as a study day or whatever. In the 2 or 3 times I've taught EMAG here, I've had a number of students, a small number, percentage wise, maybe 10-15%, take the optional final. I think only 1 has improved their grade. So we can talk about that more as the end of the semester approaches, but it's the way I have it set up. Since our last test is so close to finals week, I didn't see any value in enforcing some sort of comprehensive test at the end of the semester. So it's a choice, I suppose. Other grading elements, all things we've seen before in other classes. I suppose to pause. Anybody have any questions? Everyone's good. Regrades are via GradeScope. Again, things you've seen before. If you don't like the way something was graded, or disagree with the grading, then you can submit a regrade request on GradeScope. I guess some comment about the final. If you're looking to get points on the final, you need to actually contact me relatively immediately after solutions are posted or after it's been graded, because there's a very limited time where I have to submit final grades. Not a lot more to say here, I suppose. Everything's submitted on GradeScope. You're all well familiar with that. When we do have practical things in the laboratory, I do want you to clean up. This has become a big deal. I should actually spend a little bit more time talking about that. The chair of the department is actually kind of upset with how the laboratory is happening. And it was encouraging Mike Denmark, who many of you know, to actually police the laboratory a little bit more, and then to go after students who are leaving massive. Go after doesn't mean like we're gonna throw things at you or anything, but we will have conversations with you. So to clean things up. I suppose I've shared this before. I'm not a big fan of cleaning things up for anybody that's ever seen my apartment. And because the way my apartment is, no one is ever invited to my apartment. So I don't want to clean up after you. If I have to, I'm going to start billing you. I will charge you. You already heard this. So, and my going rate is whatever the standard engineering consulting rate is at $250 an hour. So I'll bill you by the quarter hour.
Prices are higher since last semester.
I'm really cheap. No, engineering consulting fees are much higher than that. So I'm relatively inexpensive. So.
It was $100 an hour last semester.
I've got up.
We had a project.
I want to retire earlier, so I'm charging more.
We have a project on this. It's $2 million. They want 50%.
They wanted what?
$1 million to design a facility.
Just to sketch it out on
Yes.
paper or a CAD or whatever?
Yep.
So not even to do any work?
Just the design.
I could do that. So anyway, clean up after yourselves, please. If you're gonna eat in there, make sure you don't leave crumbs and other stuff all over the place. No one wants that. I certainly don't want that. If you have to travel for any reason, for the most part, for homeworks and whatnot, we can work that out on the fly. But for tests and stuff, you really should let me know in advance. I keep forgetting to close my email. Don't need that beeping at us. So we'll coordinate all range for a makeup exam. If you need to travel for professional reasons include anything club related associated with school. So if you're going off, I don't know if anybody's involved with stuff like that, or IEEE stuff, or SWE or SHAP, or whatever the other organizations are. If you're traveling for a conference, that's very professional. Something I encourage you to do. And so we'll arrange a makeup exam, no questions. Just let me know so that I have sufficient warning so we can work out something that's reasonable. Largely, you won't need a lot of calculator work for a good chunk. Every now and then I'll ask you to crunch some numbers. By now I expect many of you have a calculator that's not garbage. So I know a lot of people have bought Inspires over the years. It's the go-to calculator. It's a good one. We'll do a lot of stuff symbolically, but I should spend more time with actual numbers, because that gives us a meaningful understanding of what relative values are. I suppose on that note, like, anybody know what the voltage difference is when lightning strikes? You have an idea?
Yeah, it's 40,000 volts or something like that.
Did I ask you that last semester?
Yeah, it was 1,000,000 volts.
Yeah, millions. So usually 1,000,000 volts per meter, roughly. So however many meters the pods are relative to their. Did I really ask you that last semester? That's funny. So that's what happens when you get older. You forget what you did yesterday. So anyway, there's our syllabus. I flew through it relatively quickly, I suppose. I did bring up my personal schedule. Like I said, this is on Brightspace, so you can find this. I am personally hoping on Tuesday and Thursday mornings to have some time to spend down in the makerspace. I should plug this a little bit more as the semester progresses. Has anybody been down to the makerspace in the last? So did you go as a tour for another class, or you just? So what, for 442 they took you down?
442 took everyone down.
Oh, so today, essentially earlier today. So it's pretty impressive what's down there. Crowded, but a lot of good stuff to have some experience with. So we want students to use it. We haven't figured out a logical way to get you in there, which is very unfortunate, but so we want you to go in there. And so I'm hoping to go in there and actually learn some of the stuff that's down there too. There are things down there that I've never used. Certainly used a lot of woodworking equipment over the years, but some of the steel stuff I haven't used, or metalworking equipment. So anyway, hopefully those mornings, I'll be down there, but I might be in my office. I'll be one of those two places. Our calendar for the class. So there's today, of course. There's no lab tomorrow. I already mentioned that. There's not a lot to dive in tomorrow. I suppose I could force you to practice mathematics tomorrow, but I guess I haven't done that in the past, so I'm not going to do that today or this semester. Scrolling down various things, you can see homework. We do have our exam one. I mentioned this already, but our exams will be on during lab session. Though I may actually have our exams over in Milne, which is that building over there that you can't see because you're all sitting down, but I can see. So it's a little bit more conducive to an exam environment. I never liked having exams in 102, which many of you had just feel it's an awkward place. stools aren't great. So I'm asking Carlene to reserve that room over there if we can. For various points in all my classes. And then looking ahead, we have exam 2 scheduled and exam 3. And then various other comments about what we're gonna study on each day. So, any questions about the calendar or anything else? Yeah.
For grade school due date time frames, like.
Yeah.
Can we do 9 o'clock,
9 a.m.
9 p.m.? 9 p.m.
9 a.m.
No.
I'm in favor of 9 a.m. 9 p.m. So you want to compromise between what did we do last semester? 6 and midnight.
Maybe.
Everybody always asks for midnight. I think midnight's a terrible time because I think you should be going to bed or I don't know, reading a book or something that's not engineering related. You like the idea of 9 p.m.?
413 gets out at 7.
So here's the important question. If I give you a due date of 9 p.m., are you gonna start the homework at 6 p.m.?
No, class at 6.
Realistically, now, everybody be honest. Who's gonna start the homework at 6 p.m. if there's a due date of 9 p.m.?
Starting at 7:30.
7, sorry, that was early.
Who starts the day? My classes go from 6.
Who's gonna start it the day, at least one day before? So, most of you, are you all being honest with me, or are you just trying to sell me a bill of goods? So. Yeah, what did you say? What's the conflict?
413 gets out at 7:29.
413. What's 413?
Power systems.
How many of you are in that class? Well. I mean, you could do my homework during his class, or they don't just. Don't do that. That's rude. Sure, we can make it. Don't share that. I don't want my other classes, so it's not going to happen in electronics. So. What's that?
It just means that you get to submit your own.
Yeah.
And then you
So-
get to.
You can start your electronics homework at 3 p.m. and start your real homework at 6 p.m. and that way you get it all.
You got next year.
It's all staggered. Yeah. What's that? Tell them I caved in the fields if they put enough pressure on me in electronics. It's not gonna happen. So. Yeah, I can make it earlier. So I don't like midnight for lots of reasons, actually. So anyway, sure, we can do 9 o'clock. Somewhere. Yeah. So there's our general. I had 5 p.m. I can make that 9. I forgot about this page, so I didn't edit this at all. But same kind of procedures that we've seen before. Prep assignments will be due before class starts on the day that they're due. And laboratories are due the following week. All our labs are all 1 week labs. Yeah, so yeah. So they're all due the following week. So a little bit more submission, but a little bit less formal, like I said. So there's our schedule. I don't know if there's anything worth looking at on Brightspace. I do have. This is something I need to address. I do have old exams. And I have, I guess 2 things to point out. I do have some crib sheets here. I really need to fix those. And so one of my goals over the next couple of weeks is to address these crib sheets. They're old. They're actually, some of it is copied from Chang. Some of it's from my advisor. I was a graduate student. And I never made changes to them. They're actually full of a lot of math. You can look at them later. It is worth pointing out. So these tests are from before I was at Albany. They are longer when I had longer test blocks. So 22 and 23 are from Albany. I suppose I could throw in my 24th. I guess I must have taught this class 3 times here. So I could add one more exam, but there is a slight difference between the way that these things are laid out. in terms of length. Hopefully the content is all pretty consistent. So just to point that out, it hasn't come up in my other classes because I've taught those classes enough that I didn't have older versions of the exams there. Oops. I don't think there was anything else worth spending time here. Everything else is structurally the same. Administration, homework, laboratories, lectures, all. I've said this in my other classes. I was supposed to just check. It is your responsibility to make sure I'm recording. So other than that, I will, as usual, upload any PDFs I'll generate or anything I've written as PDFs. So that's about it for introduction. I guess that's the syllabus day part of day one. Again, any other questions? Good class. More homework, longer homework. I figure if we're doing 9 p.m., I can actually make them a little bit longer than.
Twice as long.
Yeah, twice as long. That makes sense. From the guy who's auditing the class.
You better run when you leave today.
So, I forgot to have the conversation in electronics about what is electronics. I suppose I just thought this was a little bit interesting. It's not a little bit less relevant for you, I suppose, smaller class and all, but this is kind of the success story of how do I achieve what I want in this class. So these are trend lines to grades, not from EMAG, but I've generated these plots from EMAG as well. So on the x-axis, I have homework scores. On the y-axis, I have final grades, total percentage. Someone did score 100 on both. Perfect score in the class. Now that's an artificial data point. So if you were wondering about that in the upper right corner, that's just to make sure all my numbers came out right. But there's kind of an interesting trend line. I always feel it's worth sharing the fact that actually doing the homework and thinking about the homework, making sure you understand the homework corresponds to having a better grade. I should have generated the slope of this line. I used Excel for that, even though I hate Excel. Does it quickly enough. And I guess two things to share in terms of this plot. One, I was impressed by this, so I erased this just a second ago. But this person scoured, I think I looked it up. It was like a 4% on homework, and still managed to get like a 68, 69% class. I mean, they were slightly below average, but certainly passed. So I've had like 3 students in 20 plus years of teaching managed to do no homework and still do reasonably well in the exams, which is what that corresponds to. So that's missing 10% associated with the homework. Their number would have gone up 10% on the left just by homework. That said, I probably made this offer to you before. If you can succeed in my class without doing homework, I will take the homework part of the syllabus out of the grade calculation. I'll give you full credit if you can succeed in the class without doing any homework. And by succeed in the class, I mean get the top score on every exam. So there's the deal. Because if you do reasonably well in the exam and not doing homework, then my interpretation is if you've done the homework, then you would have crushed the exams. So the only case where I will throw it out completely is if you get the top score. And that doesn't mean you're sabotaging everyone else's score. You have to do well. So, with that said, if you're that good and you don't need to do homework, by all means, I don't want to interfere with your doing more important things. A little bit more on the negative side of things, I suppose. There's a score that has reasonably high homework scores, and I didn't look up this person. Very low exam scores. So my default assumption is if you have high homework scores and very low exam scores, that you're cheating. There's an exception to that, but if that's the case, I will subtract out your homework score and just give you a 0 on the homework. Because in my personal opinion, if you have high exam scores, high homework scores, very high homework scores and low exam scores, it means it's not your work. It's just, there's no practical reason. There's the exception, and the exception is if you're coming and asking me for help and I know you're doing the work on the homework and you're just a shitty exam taker, which is a real thing. There are people that stress out during exams, doesn't go well. Then absolutely, I give you full credit for it. So, but the correlation of finding the easy way out and then performing poorly, I don't like that. Just because I think data is interesting, I took this number and removed it. So I got rid of the person who didn't do homework and looked at how things played out. And I just like the way that line looks. It looks like a nice linear fit to the scatter data. So slope gets a lot steeper. That's because we don't have a huge sample size in our classes at all. We still only 30 or whatever points we have there. But nice linear trend there. Doing the homework corresponds to succeeding in the class more often than not. I think that's meaningful. Important data in our pictures. Pictures always tell lots and lots of stories. So, moral of the story, do the work. I suppose I didn't add this to this syllabus, and I should have. Conversation a couple of you already heard earlier today. Partly because I forgot about it. The school usually reminds. But mental health is important as well. I can add this to the syllabus. There are a number of resources available at Albany to address things that are complicating your life. Engineering can be a stressful major, so it's a lot of work, and I realize many of you are working outside of the school environment as well, so you don't have a ton of free time. It becomes important that you take care of yourself. You're eating right, sleeping well, that type of thing, as well as you can. And so there are resources, and I can add those links from my other syllabus and put a link this class syllabus as well. So I do, as you well know, give you a workload, but I am here to help you achieve success. So take advantage of me as a resource. I don't know if I must have told you this, at least in circuits or electronics, when you took that, but I am teaching faculty, so my whole role here is to be instructional. I don't have research money. I don't have graduate students or anything like that. So I interpret my role here as to help you succeed. So feel free to take advantage of me. Please take advantage of me. I get bored sitting in my office by myself staring at the wall. I like it when students, I like it when students stop by and ask questions. So anyway, there's our overview of the class, how to do well in the class. We just had some sort of discussion about doing homework. I showed you those trend lines. I think that is interesting. I suppose I can ask the question for you. Maybe you remember from physics 2, or even remember what coordinate systems there are. So what coordinate systems will we use in this class? Yeah. So polar is 2-dimensional. So we want to extend. So we did, or at least I usually consider it 2-dimensional. We do want to think in 3D. So everything we're going to do is in 3D. A lot of the math will boil down to a 1D problem. But that's because there's what we will call symmetry. So we will look at Cartesian, as you said. Our Cartesian coordinate system. And I will attempt to draw. I actually thought about taking an art class at Albany this semester. I still might, but because I can audit one class every semester. My union pays for that. Also called rectangular. Drawn a number of different ways. So the way I would draw it, often X, Y, and Z. So this is a projection that's presumably out of the paper. I'll draw this a slightly different variation of this because we'll look at this in different orientations. It should be noted that this is a right-hand coordinate system. And that has to do with the orientation of X, Y, and Z relative to each other. I suppose there's mathematics that looks at left-hand coordinate system, but we're not going to ever do that. X, again, out of the screen. And Y and Z in the screen, in the plane of the screen. So this goes back to what I said earlier is if we have a three-dimensional coordinate system, how do we represent it in 2 dimensions? It's a challenge. Hopefully we've seen this representation enough that we can kind of familiarize ourselves with it and think about what's going on. Another way I tend to draw this, and we'll do this a number of times, is I'll draw maybe Y and Z, and then I'll draw like an X there. This is a representation is out of the screen. And then symbolically, this is into the screen. So when I say out of the screen, I mean towards you. The analogy that I've always seen here, and maybe you've seen this before, is if we think of our coordinate system as an arrow. So positive direction, arrows moving in positive direction. We see the point of the arrow is just a little dot as it approaches our eye. I guess it's an unpleasant metaphor. On the other hand, if we're looking at it from the other side, we see the feathers as a crosshatch. I don't think this is a particularly good arrow because I don't know if anybody's ever shot bows and arrows. That's not what they look like at all. But I used to do that. But anyway, that's the general representation. Is that something everybody's familiar with? Just to check, kind of that kind of way out. So it is worth, I suppose, pointing out that when we look at our X range, let's change color there. Plus infinity, minus infinity. X can be anything. Likewise, Y, same thing. I bring this up because our other coordinate systems are a little bit more complicated. So X, Y, and Z, you can take any value from minus infinity. No surprises there. We've seen that lots of times. That said, what other coordinate systems are we going to use in this class, I suppose? Yes. Certainly one you should remember from physics too. Yeah. Spherical. I'm going to come back to spherical. So I like to do it third. I don't know why. So there's a variation on the polar coordinate system that I would call cylindrical coordinate. The polar is just 2 dimensions, I said, R and angle. Cylindrical coordinate system. And I need to be a little careful here, and I meant to look this up before class. The Greek letters that are involved here, I tend to forget which ones are which. I suppose let's bring up Chang quickly. So I can remember which units are used. I bring this up because these things tend to change over time. So there's our phi and z. I was going to use theta. So we do speak Greek in this class. So assuming everybody can see that, that's the phi in Greek. When I learned this years ago was theta. So I need to be careful, and I always need to look. So our phi and z. There's our cylindrical coordinate system. A little bit, unfortunately, we use our Cartesian coordinate system as a reference. So I can draw my Cartesian coordinate system again. Y, Z, and X. Forgot. When we look at R is the distance, I suppose, to qualify things. Distance from the Z-axis. So if I'm looking at some point here, and maybe it's right there, again, let's change color. That's some distance R from the Z-axis. It's some arbitrary point, again, within the limits of my artistic ability. It's not in the plane of the screen, it's outside of the screen a little bit. And it's some distance from the Z-axis. It's worth pointing out, I suppose, that this is a right angle. Again, not a particularly well-drawn right angle, but it's a right angle. So that projection, as we go from the Z-axis to whatever our point is perpendicular to the Z-axis. So again, a general reminder, it may be a while. When was the last time any of you looked at cylindrical coordinate systems, just out of curiosity? Was it physics 2? For cylindrical? Not spherical?
There's conical, spherical.
You don't do azimuth and like
We do, but
which is a weird coordinate system, but
you do different things. Well, like the standard flow, like the picture of it, that's a conical or a cylindrical representation.
Huh. Okay, yeah. Never heard of a cylindrical coordinate system? All right, so I should back up a little bit, I suppose. I kind of made the assumption that we're looking at cylindrical. We've all seen cylindrical. So here is our Z-axis. So to my, oops, change that. To minus Z, and then to plus Z. So our Z range is the same Z-axis we see in our coordinate system, or our Cartesian coordinate system. But what's fundamentally different, we can be anywhere on the Z-axis, and that can define a point. And then we rotate about the Z-axis. So that's what we're familiar with. Polar, you can maybe include that. Just as a reference, because polar is a subset of cylindrical. Polar coordinate system, which is 3D, 2D, Gordon, I said that. And we can again start with our Cartesian reference. So there's X and Y. We can pick some point, which is some distance from the origin R. So it's the same R. So we're looking at distance from the origin. But that said, if we project that point out of the paper, make it into a true 3D and just bring it straight out, then that distance R is from the Z-axis instead of from the origin. It hasn't changed at all. We've just taken this crosshairs, bring them out, bring the point out. The reference is the same. So there's some distance R, and then this is an angle relative to the positive x-axis phi. So, and that's what I'll attempt to draw on the next slide. But there's our two-dimensional equivalent projecting just to R and phi. The only fundamental difference with the cylindrical coordinate system is this whole page moves into the screen or out of the screen. And again, I find this challenging to think about it. I've done this, like I said, for a number of years. I guess I said this was the first class I taught. The other element, I suppose, is when I did my PhD, I studied electromagnetics. So it was part of my research topic. Namely, I did electromagnetic heating, microwave ovens. So I studied microwave ovens to be specific. But anyway, learning to think about how things look in space is part of our goals in this class. So I've changed my orientation. So my XZ plane is now no longer the screen. It's some plane that goes into and out of the screen. But I project this XZ plane up and down in some sense, which is a rotation of what this representation is. So that said, I can project this down to my XZ plane, so I can take this guy, project it, and there's the point. So here's our point. Oops, don't do that. Project it onto the XY plane. So this is something we do a lot of as well. We'll project onto a plane. So I take that point and I just move it straight down in the Z direction until I find the XY plane. And so I have this dashed line then. I could take that dashed line, and again, for the limits of my artistic ability, that distance is still R. So it's R from the origin now, as opposed to R from the Z axis. Again, everybody comfortable with this? That said, I can define my angle relative to the positive. Let's change colors. I don't like that color. Relative to the positive x-axis, there's my phi. So I could draw a plane up here and draw a similar angle, but that projected point in the xy plane, draw a line from the origin to where that point is, and I get an angle phi associated with it. So essentially, think of me as the z-axis. I take a point wherever my fingertip is, and I rotate it about me, and that's the angle. I move that point higher. It's still the same angle, it's just at a different z position. So we have three coordinates, r, phi, and z. And similar to what I did for the Cartesian system, where we had limits of our variables, I should point out that r has a lower limit of 0 and out to infinity. So it doesn't matter what my orientation is. Once again, if I'm the z-axis, if I'm on the z-axis, I'm 0 distance from the z-axis. But no matter where my rotation is, I can move outward, and I move outward in a positive direction, move away from the z-axis. My range of phi is from 0 to 2 pi. It is a unit circle concept. So 2 pi and 0 are the same thing. As we rotate about the z-axis, so again, using me as an example, I can rotate a full circle, 0 to 2 pi. Yeah.
We always reference the x-axis as 0.
If we're on the x-axis, we're 0 distance from the x-axis. Is that what you're saying?
Yeah.
So we need to be careful. So the reason I ask for clarification is when we're looking at phi, it's relative to the positive x-axis. So similar to our polar coordinate, here we're looking down. If we want, we could add that same thing. There's z coming out of the page. So no matter where we are relative to the origin, yes, the r distance is how far we are from the z-axis. And once again, looking at our phi coordinate, it's the angle relative to the x-axis. This isn't hugely important in terms of our mathematics, because in the long run, when we look at cylindrical problems, for the most part, phi and z will go away. There are certainly cases, and we'll talk about them, but the mathematics gets complicated where we can ask the question, if this varies as a function of phi, what happens? If it varies the function of z, what happens? A lot of times those questions are better answered in a spherical domain. So we can pick which coordinate system gives us the easiest analysis technique. But let me finish up here and I'll kind of elaborate on that in just a second. So we have z as well, and that goes from minus infinity. It's a terrible looking infinity. God dang it. Minus to plus. So full range in the z-axis. That said, I mean, I bring this up. What type of things this is for the question. What type of electronics, I suppose, exists in a spherical domain? Or, sorry, cylindrical domain? Where would we see things that are cylindrical? Actually, as I kind of look up in the classroom, I can see something that's directly relevant. As I look up. Yes, lights. Well, specific type of lights. These aren't those type of lights, so I'm lying a little bit, but. What's presumably hidden under that piece of plastic? It is an LED now. What's its shape though? So it's a long cylinder. They're replacement for fluorescent bulbs. So we've all seen fluorescent bulbs. Fluorescent bulbs are long tubular cylinders. And the analysis of the fluorescent bulb should be done in a cylindrical domain. We can ask that question. Actually, we will ask that question. What's the electric field inside a fluorescent bulb? A fluorescent bulb is a plasma. They're much more fun than LEDs. Cool things with them, especially when they go into failure mode. Like half the bulb will be lit and stuff like that. They're also toxic themselves. Or the older ones are. LEDs actually aren't particularly great either, but they do presumably last decades. Presumably. So it depends. Depends on the quality of manufacturing, I suppose, and other relative things. But cylindrical domains are relevant mathematically. Other things that are cylindrical, what's one of the fundamental things you would have seen in physics too? Wires. So a long straight wire has cylindrical characteristics, and we'll look at that exact problem. There's another thing that some of you may not have much experience with. Anybody work on older cars? A little bit. Most of your cars are new.
Also,
Yeah. So in older cars, there were, they still exist, maybe solenoid switches. Anybody heard of a solenoid switch? So a solenoid is a cylindrical domain, usually cylindrical. You can actually make a rectangular solenoid as well, but it's usually easier to make a cylindrical solenoid. And so those are the type of geometries we'll study. So reasons to do the Cartesian coordinate system. The fundamental question is, how do we solve this by hand? And so solving appropriate geometries in the appropriate coordinate system gives us an answer. I didn't ask this question with regard to Cartesian. Anybody think of the Cartesian example? There is probably one you did in physics too. What's that? No, I'm talking about where you would some electronics that would be solvable in the Cartesian domain. It's actually not a lot. What's that? Point charges are spherical, so I've given that away already. Forget the spherical, I can't accept. Yeah, parallel plate capacitors are the classic things that you would do in a Cartesian coordinate system. The shape of the capacitors don't necessarily have to be plates or rectangular plates, but it's still largely a parallel plate problem. You can do it in the cylindrical domain as well. There are probably other examples somewhat. Anybody's done any PCB work? We were talking about that at the start of class. PCB layout, so printed circuit board stuff. The ground plane circuit board is a ground plane and it's planar. So if you're going to do the electromagnetic analysis on a PCB, you may do it in a Cartesian coordinate system. That's a little bit beyond the scope of the class. That would be for probably microwave engineering, which is kind of I suppose a sequel class, elective class available with Dr. Agame. It's usually taught it. So we have our third coordinate system, our spherical coordinate system. And here my artistic stuff really comes in to be very challenging. So once again, we're going to use our reference of X, Y, and Z. I should put our coordinates. Once again, Z out of the page.
I will probably forget this. Excuse me.
What's that? Oh, I have two Z's, thanks.
But to differentiate with regard to
Cylindrical, we use a capital R, and the definition is slightly different. So want to be careful.
did I explicitly write that for spherical? Distance from the z-axis, I did. Okay. I suppose we can add the, some sense, rotation about the z-axis. Just to get that there.
And Z, of course, is movement along the Z-axis. So self-definition. When I say rotation about the Z-axis, I don't have quite enough room to space it, but relative to the positive x-axis. So if something lies on the positive x-axis, it has an angle of 0.
We said that already, but just to reemphasize that point. Here I have a capital R. So it's also a radius term. Not the. I suppose once again I should check and be consistent with Chang. Let's bring Chang back up. Yeah. Yes, theta and phi. Theta and phi. Once again, Greek.
So we have a theta and a phi.
We have our point, some point, random point. Again, off here in the space,
Not in the YZ plane. Point is somewhere out on the screen.
and the distance from the origin is our radius component now. R is the distance from the origin.
So as opposed to distance from the Z-axis, so it's distance from the origin, fundamentally different. I should be careful to use capital R as opposed to lowercase r, just to differentiate them. That we're in a appropriate coordinate system.
We can once again project. Changing colors, I suppose. What did I do before? These blue. So we can project onto the XY plane. There's our point. Projected point onto the XY plane. So same concept. And I can draw, in this case, changing colors again, some little vector. This is not R.
To the orange dash line, I guess it's hard to see the color. This is orange, the string. This is no longer R. That's R.
Not R. I'm not going to even write down not R. You can write down not R.
So it's not R. It's a different distance. It's projected. I'll give you a formula for what that length is. But
That's similar to what we just did a second ago. That's phi.
so rotation, once again, about the Z-axis. Relative to the positive X direction. So in some sense, the same phi we just saw in the cylindrical coordinates. We need another color.
And I drew this projection from the R, from the origin out to our point. We can look at that angle and move my R. And that's theta. So theta is the angle of our R vector. When I say R vector, it's the
Vector that points from the origin to our point. So the green dash line.
angle of our R vector relative to the positive Z-axis. So again,
throwing some visualization at you. And here, again, using my body as a reference where if I'm the Z-axis, there's my theta angle. So my theta angle, the angle between my head and my arm. If I move my arm up and down,
we should recognize, similar to what we did before, R can be zero distance from the origin out to infinity.
yeah,
That my plane is equal to R times cosine of 90 minus theta.
sine of theta.
That's sine.
90 cosine of 90 minus theta is sine of theta.
Oh, yeah.
And I was going to get there in just a second because we're going to flip between coordinate systems. So where were we? Theta. Theta goes from 0 to pi. 180 degrees. And phi, as before, 0 to 2 pi, 360 degrees. We can wrap all the way around our z-axis.
Excuse me. So we are under certain circumstances, it is useful to translate between coordinate systems. Again, not something I expect you to memorize.
Between coordinate systems. I will say, I usually do everything relative to the Cartesian coordinate system because that I can do off the top of my head. There are equations to transfer between spherical and cylindrical. I have no idea what they are because mostly I don't care that much. You can look them up easily enough. I think they're probably in Chang's book. But for me, it's a little bit like looking at radians and degrees. What's more meaningful for you? So as I think about Cartesian coordinate systems, it's very natural to go between Cartesian and other coordinate systems or vice versa. So I can look at cylindrical to Cartesian. I'm not dismissive of other transformations between other coordinate systems. It's just in the limit of what I have to do. Or have done. It's not that important. For other more complicated things, I've seen people do them, and it is something that's worth doing. But so essentially we're looking at this as R, phi, and Z to X, Y, and Z. Z is easy. I should change colors here. So cylindrical to Cartesian. We can start at the bottom just because it's the easiest one. Z goes to Z. Whatever Z is in the cylindrical system goes to Z in the Cartesian coordinate system. And we could write Cartesian to cylindrical as well. So just as we think about those things. We can look at our R vector, R cosine theta. So if I go and look that up, going back to our cylindrical coordinate system, here's my R vector. Remember, in cylindrical, distance from the origin to the projected point, that's still R. Both of those are R. And if we take cosine of theta, we're looking at the projection onto the x-axis. The trigonometry, that was the question that came up a few minutes ago. So if you remember, or I could go to my polar coordinate system. So here, R cosine theta, projection onto the x-axis, R sine theta, projection onto the y-axis. Yeah.
Phi or theta?
Phi. Thank you. Phi.
Yes. As I said, when I learned this, data for our polar coordinate system.
Every now and then it sneaks back in, so I do apologize. You're right. Nice, good catch. So let's erase that, put phi in there. I even wrote phi there. And here, this becomes x. And then for completeness, well, because it should be included, this becomes y. So there's our projection
For our Cartesian. And they matter if we're doing things. So a lot of the geometry analysis we will do, especially in electrostatics, will be in spherical. Some of it will be in cylindrical. A tiny bit will be in Cartesian. Likewise, when we get to magnetostatics, we'll spend a lot of time in cylindrical, a little bit of time in Cartesian, rectangular, almost no time in spherical for magnetostatics. That said, when I talked about doing my research, I did everything in Cartesian. So it didn't matter what the geometry, I did Cartesian. Anybody know why? Because I didn't do any of it by hand. What did the work for me? Not MATLAB, but the right idea. So numerical methods are used, finite element package. So MATLAB does things like that. So computers are great at doing things in Cartesian coordinates, so translating things to Cartesian. There were challenges associated with that, all sorts of research on how do you do things that are not parallel to the axes and stuff like that. But there are reasons to go from what would be a simpler calculation by hand in cylindrical or spherical to doing things in Cartesian. And we'll do that in the laboratory. So we'll have spherical problems in the laboratory, which we will do by Cartesian because we're going to use MATLAB. And there'll be some discussion of how do we improve our approximations. Because if we did all this by hand, we would get kind of an exact answer, but it would also take us 3 or 4 days. And I get complaints from students when I give them homework assignments that take more than 40 or 50 hours. So we do approximations instead and talk about those approximations and how we use them. Anyway, that's cylindrical to Cartesian. I suppose for completeness, Cartesian to cylindrical. So as we just did a second ago, we'll do x, y, z to r phi z. Z is the easy one. Go from z to z. So same coordinate. And then our r is x squared plus y squared. It's the projection to 1/2. So it's the polar projection. What's the length? If we go back to that polar coordinate system, we can project that line directly onto our polar system. What's the length of that line? X squared plus y squared square root. Pythagoras. So there's our x, there's our y. And that takes us to r. And then tangent minus 1 of y over x. That takes us to phi. So what's the angle? Inverse tangent of the opposite over the adjacent. Remember that from some trigonometry class or whatever. Again, a little unfortunate that I picked that quadrant, but there's my angle. So my opposite sign is the y, my adjacent is the x. We do want to be careful, of course, if we're using our calculator. Sometimes it gets confused by which quadrant we're in. That's a negative quadrant, that's a negative quadrant. Those are both positive quadrants when we look at the inverse tan. So we do want to pay attention to our angles. But it's not something we're going to do a lot, but I bring it up just to remind us. And then when do we end class? So in 3 minutes?
spherical to Cartesian. This is a little bit more complicated. So going back to our spherical coordinate system, there's our point. To get z is relatively straightforward, I suppose, well, somewhat straightforward, in that we're looking at cosine of theta. So we can project it's relative to this angle. So there's my angle. I project this onto my z-axis, and we're looking at cosine of theta times r. So again, writing this as, what did we do? Blue? I don't know which one was blue. Well, let's check. R theta phi to XYZ. So R cosine theta gives us our Z coordinate. To get X and Y, first thing we have to do is project this onto our XY plane. So that was the question that came up. The length of this line is r sine of theta. So my orange dashed line here projects onto the XY plane with r sine of theta. And then we can look at our phi coordinate to project onto the X and Y axis. So a lot of projecting going on. Very mathy, as I said. This class has its moments of lots of mathy things. So r sine theta cosine phi gives us our X coordinate and our sine theta sine phi. Oops, that's not a phi. Phi. Gives us our Y coordinate. There's our projections from cylindrical to Cartesian. And then not quite enough time to write our spherical one though. Once again, I don't really expect you to memorize this. I mean, it's good to know the trigonometry behind this. It's useful. We're not going to spend a huge amount of time with it, but it is something, again, to get you thinking about coordinate systems, thinking about 3 dimensions and how things look in 3 dimensions. That's the big deal, is trying to look at things in 3 dimensions. And then the associated math. We're not going to do a lot with this projection stuff. We'll do a little bit. All right. So I suppose as we're closing up shop and you're packing things up,